Okay, hi. Today I'm going to continue where I left off yesterday. I was a little tired yesterday because I had failed with the video recording because the face cam didn't sync. So today I'm recording without face cam. So I have my octave window here, and just to recap what we did yesterday. Linear regression, I have a straight line. Oh, now I don't have a pointer. Okay, here. The normal line equation looks something like this. This is the intercept term where the line crosses the y-axis, and k defines the slope of the line. So instead of m and k, we can call this these values m and k really in a way defines the line. So instead of m and k, we can call them theta 0 and theta 1 and put them in a vector. To see how wrong we are, we use something that's called the cost function. And this cost function evaluates how far we are off from the crosses with our line. If we would, for instance, guess a horizontal line down here, then the cost would be bigger. But if we do a good fit, then the cost will be smaller. So the thing here is to try to vary theta 0 and theta 1 until the cost is as small as it can be. So this is illustrated by this picture. You vary theta 0 and theta 1, and here's the cost on the y-axis, whatever you call it, the cost axis, and you try to find this point where the cost is minimal. And then theta 0 and theta 1 at this point, here is the best fit for the line. And remember, theta 0 was the intercept term, and theta 1 is the slope of the line. And to find this, numerically, you can use the derivative of the cost function. Cost function looks like this, and if you remember calculus, the derivative of something, to calculate that, you take, you have something squared, so you take the 2, move it in front, then you have 2 times this, parenthesis. And since this is in like a for loop, this sigma sign, this is sums all these terms. And this is like a for loop, and in each iteration of the for loop you have 2 times this parenthesis. So you can actually break the 2 out to here. So inside the for loop you only have the parenthesis, and outside you have 2 divided by 2 over m. And you can cancel out 2 and 2, and you only have 1 over m left. So 1 over m and the parenthesis. And now you have times x here. I really don't remember calculus so well. It was many years ago I read it, but I think it might have something to do with the partial derivatives or something. So that's where this x comes from, but I'm not sure. Anyway, it's not important. It's important that we have the formula that works. And I showed this yesterday. That's the gradient descent algorithm. It takes as input. I should say one more thing. This is the vectorized implementation, but if you don't use the vectorized implementation, you actually loop for I goes from 1 to m is the number of samples. Theta here, it's 2 values, theta 0 and theta 1, while x is only 1 value. So this doesn't really work. One value times 2 values. So to make these 2 values also, you have to add a column to this. You take the x column vector and add another column with ones in front of it. And then for each sample you have 2 values. First a 1 times theta 1, and that becomes only theta 1, and that is the intercept term. And then the x value times theta 2, and that is the slope. All right. Here it's called theta 0 and theta 1. Okay. But those 2 theta values. Anyway, stop talking, start the action. I'm going to generate the data set. First I'm going to just generate x, goes from maybe 1 to 100 points like this. I actually want to try a column vector. And I want to set y to the square root of x. Plot x comma y. Here, the square root of x. And if you do a scatter plot, write scatter instead. this actually doesn't look like a real data set. It's too perfect, so I'm going to add some random noise to this to set y to y plus some random 100 rows times 1 column. Is this correct? I think so. And do another scatter plot. Yep, and now it looks a little bit more random. And now if we will try to fit a straight line here, it will not be perfect. Let's try it. As I said, x is only 1 here, so if I say x, it should be a column of 1s first, and then the actual x values. So set this start of a matrix, then a lot of 1s, and how many? It's 100 ones, followed by the x values. That was not correct. There it is. Okay. So we have one column with 100 ones, and then the actual x values, which just comes up from 1 to 100. So this is on the format that this gradient descent algorithm expects. So let's run it. Gradient descent x, comma y, initial guess for theta 0, 0, alpha. That's a learning rate, and that is a measure of how much to change theta in each iteration. The goal here is to try to change theta to a better and better fit for each loop in the iteration. So the cost here should be lower and lower for each iteration. And you can actually plot the cost against the number of iteration, and the cost should go down like this. The cost should go down. If it doesn't go down, maybe you have a too big value for alpha, then it might go up instead. So then just try again with a smaller alpha until the cost goes down, and then converged against some value here. You can never get to 0 cost if you have try to fit a line against this data set. The cost will never be 0. Okay, that was alpha, and then the number of iterations. Let's just set 500 iterations. We got those values for theta, but I also want to check j. Theta and j. Let's see, and j goes down, and does it converge? Not really. It's still going down here, so I should maybe run more iterations. Around 5,000. Now it should converge. I should plot 1 to what the size of j, comma j. Okay, so here's the cost, and somewhere around here it starts to converge, but it doesn't quite converge. It still gets better and better and better fit here, even after 5,000 iterations. But it should be pretty good after 5,000. Let's do the scatter plot again, x, y, and then hold it, and then draw our line, which is defined by theta. That was calculated by the gradient descent here. This is the theta that is returned here. So that was the intersect, and that is the slope of the line. Okay, so let's just draw this line plot. X is just 1 to 100, and our model is theta, this intersect term, plus the slope times x. And that's it. Okay, so we have a pretty good fit here, but it's not perfect. So maybe we want a different model. So here we only have like a constant plus a value times x. Maybe we put another column here. So I have 3 with the 1s and the x, and then maybe square root of x here. Then it should be a better fit. So let's add square root of x. X is equal to x as is it now, plus another column, which should be the square root of x. Now I'll have this third column here. Right. So let's just run gradient descent again, and add another 0. For now, theta has 3. the theta vector has 3 elements. Okay, so it converged, but is it at the optimal value? It's still going down, 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 down. I think it's pretty good, but it's not perfect. Let's plot it. And now our model has changed. It's theta 1 plus theta 2 times x plus theta 3 times square root of x. Okay, so here we have a little bit better fit, and maybe if I run even more iterations, I will get an even better fit. Now this is almost 0 and this is almost 1, and that is what we want. Here. Now it's actually a good fit. This is the last one. This is actually a good fit to this data set. And we know that because we generated it ourselves. Y is square root of x. And square root of x is actually 0 plus 0 times x plus 1 times the square root of x. So a perfect fit should be 0, 0, 1. But maybe because of the randomization here, so maybe that is not the perfect fit for this random scatter here. We can check it. What's the cost of the theta? Cost of x, y, theta. 0.14. And if the cost for the perfect 0, 0, 1, what's the cost of that? It's actually a little bit bigger. So this is a better fit than what we used to generate the dots with. And that's surely because of the randomization here in the y direction. All right. And that was about it. That was what I forgot to mention yesterday. And I can add, this is still a linear regression. You just added another term, another parameter here to x. So instead of only have the constant and x, you have square root of x here. And instead of squared, you can have x squared, and then add another one for x cubed. Let's see, so then you have a constant plus a constant times x plus a constant times x squared plus a constant times x cubed and so on, and combinations of cube and square and x. Add more columns. So and then you can get like a wave line. That's called a polynomial. So if you use a higher order polynomial, you can get waves like this. But as I said yesterday, don't overfit. If you try extremely hard to go, through all the dots like this, the cost will be like 0 almost. But this will be a very strange line, and it will not predict new values very good if you have a line that goes like this, as you can imagine. So maybe this line here predicts new values better. So let's say, okay, this is our training set, and we have this last line. Use that as prediction. And we have a new value coming in. Oh, we have 90. Okay, so we go up to this. And this would be a good guess for what the y value for x equals 90 should be. Add the grid so we can see something. Grid. Now it's easier to follow here. Well, let's say 80. We have a line here. 80, and it should be somewhere between 8 and 10, around 9. And okay, now it's surely it.